Hi, in this lecture we'll be talking about potentials and lattice sums. We'll be covering parts of the textbook, chapter 3 and chapter 5. Chapter 4 is about electronic structure, and as I mentioned before, we will actually postpone those discussions until the end of the course. So last time we talked about diffusion, particularly the random walk model, and we said it provides useful information. In particular, it relates the diffusion constant to a jump rate, but in order to make this really useful, we would need to have some way of obtaining values for this jump rate R and possibly also for this correlation function that appears in the diffusion coefficient. So that provides an incentive for doing the sort of calculations that would give you that jump rate, which means atomistic calculations. Now, electronic structure calculations based on quantum mechanics could provide that sort of information, but that requires dealing quantum mechanically with all of the electrons. If we don't want to do that, then we need some way to describe interactions between atoms without explicitly describing the electronic structure. So we're kind of averaging out over that part of the problem, over the electronic problem, and just describe effective interactions between atoms. Okay, and we're going to do that in terms of interatomic potentials. So what we're going to be talking about in the first part of this lecture is the concept of these interatomic potentials and give some examples, and then also discuss how we use these interatomic potentials to obtain useful quantities such as cohesive energy, what the origin of the interactions between atoms is, and in particular we'll be talking about the Lennard-Jones potential. So cohesive energy of solids is really a straightforward concept. If we have a material in which atoms are interacting with each other, and if we have some way of calculating the energy of that system, including all the interactions between the atoms, then we can compare that energy with the sum of the energies of the individual atoms, and that gives us an energy which is the cohesive energy. So we want to express these interactions between atoms, and this is typically done in terms of potential functions that depend on number of interacting particles. So by the way, I'm talking more generically here about particles rather than atoms, because the formalism we're describing is really not limited to a case where the particles are atoms. The particles could be molecules, small molecules, or large molecules, etc. So in this potential energy, we would have a first term that simply depends on single particles. Now, essentially what that describes is if this entire system is subjected to some external force, or if there is some potential energy acting on all of the atoms, then we would need to take that into account. So that's a single particle term, which actually we are not going to be discussing any further. The really interesting part is atoms interacting with each other, and that can happen through a pair potential, which we will talking about at length in this lecture. And then there could also be interactions between 3 atoms at a time. So then you have the coordinates of atoms at positions I and j and k in this potential, and you would be summing over all those potential interactions, and this involves then a 3-body potential. And in principle, you could keep going, and also including interactions between 4 atoms, etc. In practice, the pair potentials are going to be the most important and the most frequently used way of describing the energy of the system. We'll talk a little bit next time about when you want to include the 3-body potential. So you need to write the sum over interactions between pairs of atoms, and the way this was done on the previous slide was by doing this double sum, okay, with an interaction potential that depends on the distance between particles I and j. And there are a few things you need to take into account in this sum. First of all, this prime indicates that particles are not interacting with each other. Okay, so you're excluding in this double sum the I equal j term. In addition, if you simply write a double sum like this, then you're going to have one term appearing where particle I interacts with particle j, but then there is also going to be a term where particle j interacts with particle I. And of course, that interaction energy is exactly the same and should only be counted once. So if you write it in terms of a double sum like this, you need to put a factor of 1/2 in front. Now you can rewrite this sum in different ways. Instead of putting a prime on here, you could explicitly say that in the second sum over j, you're not summing over the j equal I term. You can also avoid the factor of 1/2 by rewriting your sums. For instance, you could write the first sum as going only up to particle n-1, and then the second sum starts at I plus 1, okay? And a last way of writing this, which is kind of equivalent to this previous one, is to sum over I, but in the second sum explicitly say j is greater than I, okay? And then implicitly the sum over I will only go up to n-1. So obviously these last expressions are what you would use if you actually evaluate this in a computer code. In a computation, you don't want to do the extra work of evaluating the same interaction twice and then having to divide by 2. So here's the example for pair potential interactions between 4 particles, 1, 2, 3, and 4. So you first put yourself at particle 1, and then you have the interaction with particle 2, 3, and 4. Then you put yourself at particle 2. You do not count the interaction with 1 again. You only count your interactions with particles 3 and 4. And then finally you put yourself at particle 3, and then there is only the interaction between 3 and 4 left. So you get 6 terms, and you can easily generalize this to derive that in the case of n atoms interacting, you're going to have n times n-1 divided by 2 distinct interactions. By the way, I talk about interatomic potentials. Strictly speaking, we should always be saying potential energies, okay? Because the units of these functions are really energy, because they are being summed up to derive the energy of the system. So in order to actually do something useful, we need a functional form for these pair potentials. And basically any interatomic potential is going to have two contributions to it. At short range, at short distances between the atoms, there is going to be a repulsion. Okay, so if you plot the potential as a function of distance between the atoms, at short distances, the potential is going to become very high. And at longer distances, there is going to be an attraction. Okay, so that means that the potential energy is negative. Of course, it's going to decrease as the distance increases. It's going to go to zero ultimately. But at some intermediate distance, there will be a minimum in this potential. Okay. Now, the fact that you have a repulsion at short distance is kind of intuitive. If you bring two atoms together, they're going to start repelling each other. If you bring them too close together, there are various hand-waving ways in which you can argue about this. Kind of a semi-classical way to think about this is that as you bring them together, the electron clouds start overlapping the ionic cores or the nuclei of the atoms, therefore are less screened, and that interaction between the nuclei is what's going to cause this repulsion. Another way to think about this is that as you bring these atoms together, as I said, the electron clouds overlap. That essentially means you're forcing the electrons into a smaller space, which the electrons are unhappy about. Think about like particle in a box, where if you decrease the size of the box, the kinetic energy of the electrons goes up. An alternative way of thinking about it is that due to the Pauli exclusion principle, there are only two electrons that can go into any energy level, and so by confining the electrons more, you're going to force the electrons to go into higher lying quantum mechanical states. Whichever way you want to think about it, I think it's kind of intuitive that you're going to get repulsion at short distances. Okay. The attraction at longer distances requires some more thought and attention, and will depend on the type of interaction between the atoms. So one is going to have to come up with forms of these potentials. There are many empirical forms available, sometimes derived theoretically, sometimes fitted to experiment. A common approach is to assume a particular functional form and then fit the parameters in that functional form to experimental data or to data obtained from first principles calculations. So let's talk a little bit about this long-range attractive potential. In the next lecture, we'll be talking about different types of bonding between atoms, which could include ionic bonding, covalent bonding, metallic bonding. In this lecture, we're going to focus on kind of the simplest form, also the weakest form of bonding, which occurs in closed shell systems. which could be relevant for organics, but also for rare gas atoms such as helium, neon, etc. In this case, there is no Coulomb interaction because you have two neutral entities interacting with each other. And in fact, the long-range forces that occur between these two neutral atoms are due to fluctuations in electron clouds, and to describe this rigorously, you actually need quantum mechanics. Now, having said that, there are like semi-empirical ways of deriving these so-called dispersion forces or van der Waals forces between neutral entities. In the Drude model, for instance, you assume a shell model for the atom where you think of the electron cloud around the atom as a shell that acts as a harmonic oscillator and fluctuates around the nucleus. And of course, that creates a dipole, a fluctuating dipole, and then this dipole will induce a dipole on a neighboring atom, and then you can express the interaction energy, the dispersion energy, and if you treat that quantum mechanically, you find that it goes as minus 1 over r to the power 6, where r is the distance between the two atoms. So as I said, in principle, you need to derive this quantum mechanically. I always feel it's kind of useful to make a hand-waving argument about this. As I said, you can visualize that there is a fluctuating dipole on the first atom. Let's say we call that dipole P, an instantaneous dipole, and we know what the electric field at a distance r from a dipole is. It's the dipole divided by r to the cubed. Okay. So at the distance r, we have a second atom sitting that can be polarized. It's an atom that consists of a nucleus and a surrounding electron cloud, and that has a certain polarizability. And if we call that polarizability alpha, then we know that due to the field P over r cubed, you're going to induce a dipole alpha times P over r cubed. So now there is a dipole at this second site, which will give rise to a field at the original site, a distance r away, and again that field will be proportional to the dipole divided by r to the power 3. So in total, the field at the original site is now proportional to alpha p divided by r to the 6th. Okay, and this field will interact with the dipole on the original site, and obviously the interaction energy of this original dipole with the field will then be proportional to 1 over r to the 6th. So that's how you get this power 1 over r to the 6th. So that's the model for the long-range potential that was used for Lennard-Jones potentials. Now, when I first heard about Lennard-Jones potentials, I thought this was first described in a paper by two people, Mr. or Mrs. Leonard and Mr. or Mrs. Jones. It actually turns out it's one person with a hyphenated name, John Edward Lennard-Jones. who is immortalized by having this potential named after him. So, as we discussed, the long-range part is proportional to 1 over r to the sixth, is a minus sign because it's attractive, it lowers the energy. And then Lennard-Jones had to come up with a short-range part of the potential. So it needs to be repulsive, it's going to be positive, and actually, realistically, based on quantum mechanics, you expect that repulsive part to be proportional to an exponential. It should exponentially rise as the distance decreases. Now, that actually becomes mathematically complicated. So what Lennard-Jones did was come up with a simple polynomial form, just 1 power of r, and he chose 1 over r to the 12th, 12 being double of 6, which actually, as we will see, makes it computationally quite convenient to work with. So there is no particular physical justification for the power 12. It just leads to a strongly repulsive potential, and it's convenient. Okay, so the total potential then has 2 terms that are written here with these arbitrary coefficients a and c. Now, this is not the form in which this potential is usually written down. It's usually written down in terms of 2 other parameters, epsilon and sigma, that if you pair, you can express in a and c in terms of epsilon and sigma. But these epsilon and sigma parameters have a distinct physical meaning. Clearly, when the distance r is equal to sigma, the potential is 0. Okay, so sigma signifies the distance at which the 0 crossing occurs. And it turns out that if you minimize the potential, you find the value at the minimum equal to Rm, m for minimum, and the value of the potential at that minimum turns out to be minus E. Okay, so you can do a simple derivative, set it equal to 0, find the value of Rm, which turns out to be sigma times 2 to the power 1/6. Okay, you plug that in and you immediately find the value of the energy is minus E. Okay. Now, once you found this value Rm, since Rm is related to sigma, you can rewrite the potential, if you will, in terms of Rm instead of sigma, and then you come up with this expression here. So, as we already mentioned, because the long-range attractive potential is designed to work for closed shell systems, it's going to work quite well for rare gas atoms. Okay, and this is illustrated here. The solid line is actually an experimental curve that's derived from performing molecular beam experiments. The dashed line is the Lennard-Jones potential fitted to the case of argon. And well, you see, it's not bad. There is some quantitative difference. Because you only have 2 parameters to fit, you can't do the fitting perfectly. But in the long range, the functional form is quite well described. The minimum energy is a little bit too shallow and the repulsion isn't quite right. But overall, this does a decent job. Okay, and by fitting to experimental data like this, you can obtain these values of epsilon and sigma for all of the noble gas atoms. So It's probably fair to say that the Lennard-Jones potential is the most frequently used interatomic potential. Not because it does a terribly good job, but because it's so simple. We will see that you can actually do quite a bit with it just analytically without having to write any computer code. And even for a computer code, if you want to do a molecular dynamics simulation or any of the type of simulations that we'll be discussing later in the course, the cost of the calculation is going to depend on how expensive it is to evaluate these interatomic potential energies. And because the Lennard-Jones potential is so simple, it's quite cheap to run calculations with it. So even if ultimately you want to have a better description of your material, very frequently when first writing a code for a particular application, people write it for this simple potential for testing purposes. So because this is kind of the most simulated material using these atomic potentials, you can jokingly refer to it as Lennard-Jonesium. So, as I already said, the main reason why it's so widely used is because it's so easy to use. It has a simple form. It does have the general features of a real potential. It has the repulsive and attractive terms in it. And because it has been so widely used, there's kind of a networking effect that more and more people use it because there is a wide database of simulation data already available that is useful for comparisons. So in this course as well, we will essentially use it as a generic potential. Okay, so we talked about these two parameters that occur, epsilon, which has units of energy, and sigma, which has units of distance. And that actually suggests that we could rewrite the potential in so-called reduced units. Okay, if you divide the potential, which has units of energy, by this parameter epsilon, and you divide the distance r by sigma, then you come up with these starred variables that are dimensionless. And then you can write the Lennard-Jones potential in these reduced units, and it simply looks like this. Okay. Now, for the purposes of writing the code, this is quite convenient. You don't need to carry these parameters around, okay? And then at the end of the calculation, you can always convert back to the variables that do have units simply by replacing the start quantities with the original quantities again. Okay. But this immediately tells us something important, namely that when we do the simulation in these reduced units, it is applicable to all systems that are described by a Lennard-Jones potential. Okay, meaning that it doesn't make sense to say that you separately do a simulation on Lennard-Jones argon and a separate simulation on Lennard-Jones neon. It's really the same calculation where you can scale the results. Okay. So this may seem kind of obvious, but you can actually find quite a few examples in the literature where people think of these two simulations as kind of different things, which they're really not. The code, the simulation is the same, it's only the interpretation. Once you plug in the specific parameters, that is different for these two materials. Okay, so we talked a little bit about the potential energy of solids. We talked about the Lennard-Jones potential, and now we're actually going to go in a bit more detail about how you use the Lennard-Jones potential, or any other potential for that matter, to execute lattice sums, which may involve doing infinite sums, which means that we're going to need to make the sum finite by introducing a cutoff. And then we also talk about periodic boundary conditions, which actually will allow us to simulate, as we will see, non-periodic systems. Okay, so back to lattice sums. Now that we have like one specific interaction potential in mind that we can use as a generic example, we can talk about actually evaluating energy. So we already said in the example of the cohesive energy that you express it in terms of these potential functions. We're going to need sums over pair potentials, and in principle in a large system n is very large or even goes to infinity, so we will either need to find approximations, or actually one of the neat things about the Lennard-Jones potential is that you can do the sums exactly, as we will see. Okay, so doing this exactly or analytically is actually unique to Lennard-Jones solids. Okay, solids described by a Lennard-Jones potential. But the procedure that we will show will nicely illustrate the process of energy minimization. We are going to do the lattice sums for the 1 over r to the power n potentials analytically, or actually we're going to use published results that were derived analytically. But of course, for a general interatomic potential that has a more complicated mathematical form, this will no longer be possible analytically. You're going to have to write a code to actually evaluate it. So let's say we have a solid which consists of a periodic repetition of unit cells, and within each unit cell you have lowercase n atoms. Okay, so this is the so-called basis. Your lattice is described by lattice vectors capital R, and within each unit cell you have a certain number of atoms, in this case 2, that form the basis. So we obtain the energy of the system, as we said before, by doing a double sum over all of the pairwise interactions between atoms. So we're limiting ourselves now to pairwise interactions. We're for now not worried about 3 or 4 body interactions. So this is the double sum that we need to evaluate. Remember, the prime means that atoms do not interact with themselves, and the 1/2 is there to avoid double counting interactions between atoms I and J. Okay. Now, if the lattice vectors are described by these vectors R, and if the positions of the atoms within the unit cell are described by lowercase r, then you can rewrite this energy like this, okay? And you might naively expect that there is going to be a double sum over the lattice vectors are as well, but actually it's not a double sum, it's only a single sum, because we have switched from describing the energy for the entire system to describing the energy per unit cell. Okay, so we're basically placing ourselves in one particular unit cell, and we're looking at the two atoms within that unit cell and then counting all the interactions between these two atoms and all of the other atoms within the system. Okay, so that's one way of thinking about why there is only a single sum over lattice vectors here. An alternative way of thinking about it would be to write out the first line explicitly, which would give you a double sum over all of the lattice vectors. But then you can rewrite the summation over lattice vectors by switching to a different variable, which is the difference between lattice vectors, and that will also then mathematically show you that this expression is the correct expression. You may want to do that as an exercise. Another nice exercise is to start from this general expression, and while this was written for the general case where there are n atoms within the unit cell, you can write it for the case where there are 2 atoms in the unit cell. So these sums then simply run from 1 to 2, and as an exercise, please check that this results in an expression that has these 4 terms. The summation over I and j, which is now just running over 1 and 2, has been written explicitly, and the only remaining summation is over all the lattice vectors, capital R. So that was written for a general potential phi. Now we're going to apply this to the case where the atoms are interacting with a Lennard-Jones potential. We're also going to do a simplification and assume that there is only 1 atom per unit cell. Okay, so the primitive cell of our solid only has 1 atom per cell, and that would happen, for instance, for a cubic system such as face-centered cubic. Okay, so face-centered cubic, of course, is described by these 3 lattice vectors for the primitive cell. And in this simple case where there is only 1 atom per unit cell, there are no additional sums involving summing over the atoms in the basis. The energy per cell, which is now written as lowercase u here, simply consists of evaluating this sum over the lattice vectors in this generic form. It explicitly says the atom is not interacting with itself, obviously. The unit cell of interest is not interacting with itself, but other double counting is avoided by the factor 1/2. And we can now plug in our Lennard-Jones potential, which looks like this. Now, it used to have the prefactor 4 epsilon, but because of the factor 1/2, it's now only 2 epsilon. Okay, so we need to sum over all of the lattice vectors, for instance, in an FCC structure. And notice that in the form of the potential, we don't actually need the vectors, we only need the length of the vectors, the magnitude of the vectors. Okay. And it's actually convenient when treating these lattices to factor out the distance parameter characteristic for the crystal, and you could either factor out the lattice constant A itself, or you could factor out the nearest neighbor distance, Rnn, which is simply the lattice constant divided by square root of 2. Okay. So these magnitudes of the lattice vectors, which I've simply written here as capital R, as a scalar, is actually a typo in the book where this is written as a vector, but it's actually just a scalar, is going to be proportional to the nearest neighbor distance times a dimensionless quantity, which of course depends on the lattice vector. There are going to be shells of neighbors. For the first shell, the nearest neighbor distance is Rnn, but then in the second shell, alpha is a bit larger, etc. Okay, so for all of the shells of neighbors, you have a specific value of alpha. So the sum that we need to evaluate here has the generic form of being a sum over terms that are 1 over r to some integer power n. Okay, that's what we need to evaluate. And because we can factor out this nearest neighbor distance, we can bring 1 over r nearest neighbor to the power n outside, and then we have a sum over all of the lattice vectors over terms that are these 1 over alpha to the power n. Okay. So sometime in the last century, somebody figured out that you could obtain a closed value for these sums. You can evaluate this analytically. Of course, it depends on the crystal structure. I said for FCC, these distances to various shells of neighbors have specific values, and it would be different for BCC or a hexagonal system. But for various crystal structures, these sums have been evaluated. Here's the form written down as a series for FCC, and then you can explicitly sum this. Okay, and these sums have been tabulated for the infinite summation for 1 over r to the n potential, so for various values of this power n, but only for n larger than or equal to 4. Okay. Next time we'll discuss why there is this restriction. So the evaluation is due to Jones and Ingham, and they used a trick that's peculiar to these 1 over r to the power n potentials. It's a bit similar to evaluation of Ewald sums, which we will also talk about next time. So you should read section 5.11, where this is discussed in a bit more detail, and the resulting values are tabulated like this. Okay, so it was done for simple cubic, body-centered cubic, face-centered cubic, and only even powers of n are listed here, but it includes the n equals 6 and n equals 12 that you need for the Lennard-Jones potential. So that means that in the case of a Lennard-Jones solid, you can have an analytical expression for the energy per unit cell. Okay, and of course it depends on the parameters epsilon and sigma that depend on the particular material you're simulating. It depends on the nearest neighbor distance obviously, since the Lennard-Jones potential does. And then you have these factors A12 and A6, which are the sums that come out of that table. And these sums would be different for simple cubic, FCC, and BCC. Okay. So if you think about it, the only variable that contains information about the structure of the solid is the nearest neighbor distance, R and N. So we can plot this energy as a function of R and N. And not surprisingly, it kind of has a form that looks very similar to the Lennard-Jones potential itself. Mind you, it's not the Lennard-Jones potential, it's a sum over all of these pairwise potentials that are Lennard-Jones potentials. Okay. So in this plot, you can make this plot generically for like dimensionless units, if you will, or you can pick a specific value of epsilon and sigma. But what was done in this figure here is compare the form of the plot for the three possible structures, simple cubic, FCC, and BCC, for which these values of A6 and A12 were tabulated. And a nice and interesting result is that FCC is the most stable structure, which is actually experimentally correct for the rare gas solids. Once you have a curve of U versus the nearest neighbor distance, you can evaluate various other quantities of interest. In fact, what you first want to do is rewrite the expression in terms of the volume of the unit cell rather than the nearest neighbor distance. That's an easy piece of math to do that replacement, and then you have a U function as a function of volume V, okay, and then you could evaluate the minimum, okay. You could do the derivative as a function of R and N or as a function of volume, and you find the equilibrium nearest neighbor distance or lattice parameter or equilibrium volume. Another interesting piece of information is that you can find the pressure in the system, okay. So at the equilibrium volume, the pressure is obviously zero, but at other volumes there is going to be a finite pressure. In particular, when the volume is smaller than the equilibrium volume, there is a positive pressure, right? So the pressure is defined, in fact, as the derivative of the energy with respect to volume, with a minus sign, okay? In case you have trouble remembering this expression, you can use as a mnemonic what I just told you, namely that you know the pressure is zero at the equilibrium volume. How do you find an equilibrium volume? You take a derivative, right? And then to remember the sign, all you need to remember is that as you compress the material, delta V is negative, and that's going to correspond to a positive pressure, right? So you need a negative sign in this expression. Now, the pressure is a quantity of interest, but what's also very interesting is the bulk modulus of the material, okay, which gives you some physical information about how the material behaves. And the bulk modulus is defined by taking another derivative, the derivative of pressure as a function of volume, okay, and multiplying that by the volume and taking the value at the equilibrium volume. Okay, and since we can express pressure in terms of energy through this derivative, we can plug in this expression for pressure and find that the bulk modulus is proportional to volume times the second derivative of energy with respect to volume at the equilibrium volume. So this effectively evaluates the curvature. Okay, a high bulk modulus means that the energy changes very rapidly as a function of volume in the vicinity of the minimum. So that's going to tell you that the material is very hard, right? The energy goes up quickly as you try to change the volume, meaning it's very difficult to change the volume. So that's a hard, a stiff material. So again, in order to remember this expression for the bulk modulus, one thing that I keep in mind is that the units for bulk modulus are the same as pressure, gigapascal or megabar, if you will. And clearly that means that in these expressions you need that factor V to make the units work out. Again, in terms of remembering what the sign is, the bulk modulus obviously is defined as a positive quantity. So since the energy is a minimum in the vicinity of the equilibrium volume, the energy can only go up. So the second derivative is going to be positive, and the volume is positive, so that gives us indeed a positive value of the bulk modulus. So as we said, the equilibrium nearest neighbor distance is where the derivative with respect to the nearest neighbor distance is 0. That immediately gives you a value for that minimum nearest neighbor, for that nearest neighbor distance in equilibrium. It's called R0 here. You can express it in terms of A12 and A6. And in the case of FCC, that turns out to be 1.09 times sigma. And then you can evaluate the energy at the minimum, and it turns out to be minus 8.6 times epsilon. And you can evaluate the bulk modulus by taking the second derivative and find this expression here. So clearly, for the Lennard-Jones potential, or for that matter, any potential that only contains 1 over r to the n terms, you can do all of this analytically thanks to those tabulated values and get properties of the material, at least at t equals 0, where you don't need to worry about entropy, etc. It's just energies. You can get these properties very easily. So in the last part of this lecture, I want to talk more generally about lattice sums, because the fact that we could do things analytically in the case of the Lennard-Jones potential is kind of a fluke, because the potential is so simple. Any more complicated potential will require you to write the code to computationally evaluate the lattice sums. Okay. So let's first talk about perfect solids. They are perfectly periodic, and if you want to get the properties of the solids in principle, you need to sum over an infinite number of unit cells, but of course in the code you can't do that. Okay. So in practice you're going to truncate the summation, and the way this is typically done is by truncating the potential. Because as we already said, the long-range part of the potential is going to go to 0 in some way, and if it hopefully goes to 0 fast enough, you can do the truncation and only make a small error. Okay. So in this sum over lattice vectors, you're not going to sum over an infinite number of vectors. You're going to cut it off in some way. So what that means in practice is you put yourself at a given atom and you evaluate the pairwise interactions with all other atoms, but rather than including all atoms out to infinity, you only include atoms that lie within a given cutoff radius RC. Okay. So obviously in doing this, we're making an approximation. Okay, we are ignoring all of the interactions with atoms outside this cutoff radius. How big is this error? Well, it depends on the cutoff radius. The larger the cutoff radius, the more accurate your result is going to be, but the more work it's going to be. So it's a trade-off. And the size of the error also depends on the potential. How quickly does the potential fall off as you increase RC? Okay. And in practice, when you actually program a situation like this, you're going to need to test whether a given value of a cutoff radius is sufficient, and you do that by increasing the cutoff radius and seeing whether the results change. Now, again, because in the case of Lennard-Jones, exact results are available, it makes a good test case. Okay, so as part of the upcoming assignment, you will actually do this as an exercise. So in practice, you can kind of think of this cutoff as you have the full form of the Lennard-Jones potential, but then at a given cutoff radius, you just set it to 0. Okay, and well, that means that certain interactions are not included. It's going to lead to a finite error, and you can evaluate how big that error is for the quantities that you're interested in. So we talked about periodic solids in which you have unit cells that are periodically repeated, and then in principle you need to do an infinite sum, but it's going to be a finite sum. Now, this notion of using periodic boundary conditions is actually very useful, much more useful than just applying it to the situation of crystals, which have actual periodicity. You can apply it to any situation where you want to simulate a given set of particles or atoms that are interacting with each other. For instance, if you wanted to figure out how these 7 particles interact with each other, well, you know that they're part of a larger system, but you can't actually afford to simulate more than 7 individual particles. So what you do is you set up a simulation box, which is your new unit cell, and you periodically repeat that unit cell, filling all of space using periodic boundary conditions. Okay, so this notion of using periodic boundary conditions, often called the supercell approach, actually allows you to simulate anything. Simulate things that do not intrinsically have periodicity. Okay. You could simulate an individual atom or a molecule, if you will, by placing a single molecule in the center of a box like this and then periodically repeating it. Okay. You could simulate defects in solids because a point defect breaks the periodicity. You no longer have the perfect lattice. So you would have like a periodic array of atoms, but maybe with one vacancy in the middle. And in principle, that vacancy in the dilute limit would be sitting in infinite solid, but you cannot afford to have an infinite number of atoms in your simulation. So you put the vacancy in the middle of a finite number of atoms, but then you still want to simulate an environment in which you have a solid. So with that finite number of atoms, if you just had vacuum outside, that would not be representative of a solid. So what you do is you take that finite simulation system and you replicate it using periodic boundary conditions. But of course, this is all at the expense of having, for instance, a defect present in every cell. Okay, so there may be potential interactions between these defects. And the final example is, well, you could simulate a liquid. The atoms that you put in this simulation box do not need to be in a periodic array. They can have any position as they are in a liquid. But again, instead of having this finite number of atoms sitting in vacuum, you replicate this simulation box. Okay, and then in the case of a liquid, you're probably going to be interested in the dynamics of the atoms, but you then have to remember that if atom 1 moves, that all of the atoms 1 in each of these replicated cells will move. Okay, so obviously your box is going to need to be big enough so that correlations in these motions are not going to play an important role in the results of your simulations. Other things to note about the supercell approach. Well, if during a dynamics simulation your atom 1 would move and it would move outside the central box, that doesn't mean it's gone. Due to the periodic boundary conditions, it will reappear on the other side of the box. Okay. Another thing to keep in mind is that the simulation cell that you choose must be space filling. Okay, it must have enough symmetry so that you can fill all of space by periodically repeating it. And for that reason, these simulation cells are basically in a standard way chosen to represent standard lattices, okay, like cubic lattices. Okay, so that's the concept of supercells and periodic boundary conditions. Now within that concept, we're still going to need to choose a cutoff to be able to write code that runs in a finite amount of time. Now, the supercells that are often used for molecular dynamics simulations or Monte Carlo simulations, which we will be talking about, often have very large numbers of atoms. And well, in the simulations that you'll do for the homework assignments, maybe there will only be a few hundred atoms, but in realistic simulations, sometimes people have millions of atoms. Okay, so obviously you cannot and you don't want to do sums over pair potentials for millions of atoms. So you need a cutoff in the potential. Okay, and well, as I already said, it's a trade-off. You want to choose that cutoff so that you have sufficient accuracy, but you don't want it to be too large, to be too expensive. But let's say you've determined a reasonable range of this cutoff energy. That means that for every atom you're looking at, you're going to need to evaluate interaction terms with all atoms lying within the cutoff radius, but that means you have to first determine which atoms lie within this cutoff radius, okay? And that exercise by itself could become quite expensive if your simulation cell has so many atoms, okay? So you really only want to have to do that test to test whether a given atom lies less than RC away from the central atom. You only want to do it for a finite number of atoms, a relatively small number of atoms, and typically in order to do that you choose a box that's centered on the central atom, and you only consider atoms within that box. So the sides of the box are essentially 2 times RC. You will still need to run the test because there will be atoms kind of in the corners of the box that should not be included when you calculate your interaction energies, but at least it's only going to be a finite number of atoms for which you need to check this distance. So that means we are now in a position to actually evaluate these energies. Remember that if it's no longer a crystal, but kind of this more general situation for a liquid or whatever it is that you're simulating, these lattice vectors are now for the simulation cell, the supercell. You're going to cut off the potential. You're going to use this approach where you choose a size of a box equal to 2 times the cutoff radius to limit the search over the atoms that are going to be included in the simulation. In the case of small or modest size systems, what you can actually do is to choose this search box to have the same size as the simulation cell. Okay, kind of makes intuitive sense because the sides of the search box are set by this cutoff distance, and if you would actually make the search box larger than the size of the simulation cell, then you're actually including interactions with atoms in a neighboring supercell. But these atoms are not really new atoms. These are atoms that are already included in your first simulation cell. Okay, so you're in a sense doing some kind of double counting that is not quite physical. So that's why limiting the size of the search box to the size of the simulation makes sense, and that is typically referred to as the minimum image convention. Okay, so in this example here, where indeed we have a modest size simulation cell, let's say that we would figure out the interactions that atom 1 has with surrounding atoms. We're going to limit the search over atoms that are going to be included in the sum, 2 atoms that lie within a box with the same size as the simulation cell, centered on atom 1. Okay, and that makes sense because, for instance, if we made that box larger, we might be including an interaction between this atom 1 and this atom 5. But look, atom 5 is actually already included in the original box. Okay, so you don't really want to include atom 5 again. So for modest size systems, this is very simple, efficient, makes a lot of sense. But as I already said, if you have much larger systems, thousands or millions of atoms, clearly you want to choose a search box that is much smaller than the simulation cell. A few words about the choice of the simulation cell. You could choose a cubic cell because it's simple, but you don't have to do that. You could use any symmetry of the cell. It's usually recommended for programming purposes to write positions of atoms in fractional coordinates, fractions of the cell parameters. That is an approach that is followed in crystallographic tables, for instance. We call the lattice vectors by vectors A, B, and C. For a non-cubic system, there are going to be angles between these lattice vectors. And, well, a particular position of an atom can then be expressed in terms of, for instance, these fractional coordinates 1/2, 1/2, 1/4, which would mean that the position can be expressed as 1/2 lattice vector A plus 1/2 lattice vector B plus 1/4 lattice vector C. Okay. So I'm going to go through this fairly quickly. You could set this up for FCC. We already talked about the lattice vectors. The fractional positions would be L, M, N. You can express those as a vector S. And the real position of the atom would then be LA plus MB plus NC. Now we can use the lattice vector A, B, and C to build a matrix where the coordinates of the vectors A, B, and C form the columns. And once we have that matrix, then the vector that determines the real position of the atoms can be expressed as this matrix multiplied by the vector that represents the fractional positions. So, in general, this vector H would have 9 components, and this is just an enumeration of the sort of operations that you can do with vectors and matrices. You can take the transpose, you can take a vector determined by its components, take its transpose, and hopefully you're familiar with all of this linear algebra. You can do a vector times a vector dot product, which in terms of this notation would amount to taking the transpose multiplied by itself, and that gives you indeed the correct result for the dot product, and multiplying a matrix times a vector results in an expression like this, where each of the components of the resulting vector can be expressed based on matrix elements and components of the original vector A. So this matrix A is this matrix that consists of the lattice vectors, and I encourage you to read about this in section B24. Okay. For a general crystal system, as I said, the lattice vectors are going to have particular orientations that may differ from the Cartesian axes. So there are angles between them. They have a specific magnitude, A, B, and C. And in terms of these magnitudes and angles, you can then write down this matrix A generically in terms of the magnitudes A, B, C, and these angles. Okay. For a cubic system, of course, it's very simple. You have three orthogonal lattice vectors, each with length A. For a monoclinic system, the lattice vectors have different lengths, A, B, and C, and there is an angle beta. And so you can do this for any crystal system. And once you have your problem set up this way, your matrix A summarizes all of the information about the lattice vectors. The positions of atoms are then determined by these vectors S, fractional coordinates. And if you want to evaluate the distance, you would need to evaluate r squared. You can express it like this. You rewrite a little bit, and then you come up with an expression that involves this quantity g, which is the so-called metric tensor. Okay, which again only depends on the length of the lattice vectors and the angles between them. Okay. So this illustrates that working with fractional positions of atoms within the unit cell is really useful because once you have written your code in terms of these fractional positions, you can basically apply it to any crystal symmetry simply by plugging in a different form for this metric tensor. And you can always go back to the full positions of the atoms by invoking the relationship based on the fractional coordinates and this matrix H. So, cubic cells are simple, but you can use cell with any symmetry as the simulation cell. We have talked about periodic boundary conditions, using cutoffs, using search boxes, and how to do sums. And next time we'll illustrate how to use all of this formalism to actually calculate useful quantities.